You did it.
Progress, we're good. Can you still hear me?
Yes.
Okay, good, good. All right, now let me get back to my introduction slide, if I can remember how to do that.
You gotta continue up on here.
Oh dear, look at that.
Got to do what?
You gotta continue.
This meeting is being recorded. Continue.
That's on the other.
Okay,
Host should be able to share your screen with the introductions.
Has he exhausted?
is anybody seeing this?
Walked out of jail,
Yeah,
got out of jail
yeah.
No, I'm just seeing people.
4 times,
Why?
right? There's a gang of people didn't like him.
You gotta share it again.
She got down. Mhm.
That's
Okay, something happened. Yep, there you go.
Okay, all right. So I think we're ready to go here. If everybody's seeing my introduction slide, I'd like to introduce our speaker tonight, Luci Finucan, is an educator at the Green Bank Observatory in West Virginia, where she teaches thousands of students a year to operate radio telescopes. That's what I want to do. And she hosts weekly multicultural planetarium shows and directs the Pocahontas County Science and Engineering Fair. So she's into a lot of outreach activities here. She's currently pursuing a master's degree in education with a focus on science literacy at Marshall University in Huntington, West Virginia. And while pursuing her degree in physics at Virginia Tech, she did research at the school's Center for Communicating Science.
Oh,
She's also volunteered at the Smithsonian Air and Space Museum in Washington, D.C., which is also a really neat place if you want to go to a really cool museum. That's a great one. She completed an education outreach internship with the Center of Science and Industry in Columbus, Ohio. And the one story I think is one of her best qualifications here, her interest in science began early when she practiced reading with her father from what she described as a quote unquote, admittedly outdated astronomy encyclopedia. When they got to the chapter about the Big Crunch theory, 6-year-old Luci began sobbing at the thought of everything imploding in on itself. But not to fear, her father comforted her in the only way that a father can comfort. He said, "Don't worry, we'll all be long dead by the time the universe collapses." So she got an early start, and she is relieved to know now that new data suggests the universe may not collapse in on itself after. So maybe we don't have to worry about
Actually, the big rip gives me the willies.
that. Okay. All right, let's see. How do I move this ahead? Okay, so tonight's program is going to be a virtual tour of the Green Bank Observatory. For more than 60 years, the Green Bank Observatory in West Virginia has served as a center for radio astronomy and related research. It is home to the 100-meter Robert C. Byrd Green Bank Telescope, the world's largest steerable radio telescope,
She was gonna
as well as 7 other radio telescopes.
okay.
And there's a picture of the 100-meter telescope there. It is really fantastic machine to see. And so with that, I would like to turn it over to Luci. Welcome, welcome to our meeting, and I'm going to stop sharing here and turn it over to you. Let's see.
Yeah, I did. Thank you for sharing that. I still have one of the, this is the encyclopedia book that was from that story when I was still learning to read. Quick question. When I was talking with Sarah, she said that you guys would prefer the GBT tour. Would you prefer to learn about the telescope itself or the site? Because I can do either.
Can you, yeah, both of those topics sound very interesting. I mean, if you can do both, can you give us a little bit of each, or what does the group think?
I'd be more interested in the telescope than the site, but interested in both, really.
I mean, you might just have to have me back to do the other one.
Yeah, we might
There
do
you
that.
go.
Okay.
Problem solved.
All right. So
Here she is.
I am still working on trying to get my PowerPoint open, but while I am doing so, I want to talk a little bit about the history of Green Bank. So we are a radio observatory in Green Bank, West Virginia, right smack in the middle of nowhere. But that's on purpose. And there's the reason for that is all of you guys in civilization give off a lot of interference. You give off, anytime you use a cell phone, a computer, your car, your radio, your oven, a light switch, you give off a little burst of radio energy. And our telescopes, which are the most sensitive in the world, can pick that up, which causes a bit of an issue. This is very similar to the idea of light pollution, right? But with light pollution, if you get everyone to point your street lights down, you can really mitigate that interference, right? The issues that causes. Radio interference, unless you can get everyone to use a Faraday cage around their house and their car and their cell phone tower, you're not going to be able to really protect your telescopes from that interference. So it was decided that if the United States was going to have a national radio astronomy observatory, it would have to be as far away from people, technology, highways, civilization as possible. And that's where Green Bank, West Virginia comes in. So we are in the middle of the National Radio Quiet Zone. And what this means basically is if you want to build a cell phone tower, a radar station, a radio station, any permanent radio transmitters within this 13,000 square miles, you have to, of course, get FCC approval, right? You have to get Federal Communications Commission approval, but you also have to get Green Bank Observatory approval. And if you want to build something, super far away, like over here in Harrisonburg or down here near Roanoke, no big deal. But if someone wants to build a cell phone tower right next door in Durban, we can say, no, you can't build that. However, Pocahontas County has one of the lowest population densities of a county east of the Mississippi River. We don't have a lot of friends. We like to be nice to people. So usually we won't say, no, you can't build that. What we like to say is, here are some changes we would like for you to make to your design. And usually this is, hey, use a different frequency we're not interested in. Use less power so your signals don't reach us. But most of the time, we say, can you move your site that there's a mountain between us and you? So we are in the county with the highest average elevation east of the Rockies. We're right here in Deer Creek Valley, Pocahontas County. And all of those mountains protect us from a lot of that interference. And you guys know this because if you've ever been driving around in the mountains, you'll be going around one side of the mountain and you got cell phone signal, you're listening to the radio, everything's fine and dandy. And then you'll go along the other side of the mountain, and all of a sudden you're just listening to static and you don't have any cell phone signal, right? That's what happens in the mountains. And that's because mountains are really good at absorbing that radio energy. So that's one of the reasons why Green Bank was chosen to be the site of Green Bank Observatory. In addition, we have one of the lowest population densities, like I said. So we don't have a lot of people here, and fewer people, excuse me, means less interference, and less interference means better data for us. So we have a whole lot of telescopes. We have, a dozen or so. This is the 300-foot telescope, finished in 1963. And when I call this a 300-foot telescope, that means that it's about a football field from this edge to this edge. It is ginormous, and it was a very, very sensitive telescope that was doing a whole lot of astrochemistry and structural mapping research. Now, this telescope was only built to last for 5 years, but it ended up lasting for 25. So this is a picture of the telescope that was taken in 1988 on November 15th. And this picture was taken before 9:43 p.m. And I know that this picture was taken before 9:43 p.m. because that happened at 9:43 p.m. Yeah, this was not planned. I did this talk to a group of like engineering people, and the guy goes, "That doesn't look like a controlled demolition." And no, it was absolutely not a controlled demolition. The telescope just collapsed. What ended up happening was one of the joints in the center of the telescope failed, right? It just rusted open. The rest of the telescope failed with it. But this was a problem, because there were people whose job depended on this telescope. There were people who were employed to operate, update, maintain this telescope. There were projects that we were doing on this telescope, and suddenly we just didn't have a telescope anymore. So we needed a new one, and we needed a new one fast. Construction on the Green Bank telescope began in 1990, went until the year 2000. First light was in 2000. First observations began in 2001. The Green Bank telescope is the world's largest fully steerable radio telescope. And it is the third largest movable structure on land. It is ginormous. Of course, that's not including boats, right? It is 485 feet tall. It's 30 feet taller than the Great Pyramid of Giza in Egypt. It weighs 17 million pounds and can rotate 360 degrees in 9.5 minutes. It has a 2.3 acre dish, which is about 6 Olympic-sized swimming pools. Here's a little map of our site, a satellite image of our site. This is the Green Bank telescope. It's 100 by 110 meters. We have a couple other telescopes. This is the 140-foot. Over here, we have the 85.3 and the 85.2. This is the 40-foot telescope. We have the Tatel telescope, the 85.1, etc. We've got 20-meter. Over here, this is where I live in Arbavale, right next door. Here we have the Science Center, and that's where you're going to go if you guys ever come visit me. And then right here, this is the Jansky Lab, named after Carl Jansky, who discovered what he called star noise coming from the center of the Milky Way galaxy. And that's where our telescope is controlled from. So we have the control room. These 4 screens are what allow us to pretty much do anything we want with that radio telescope. This one right here is a lower level software situation. So if something in these 4 screens breaks, we can go to this one before we have to start messing around with hardware. These big scary looking buttons over here, the yellow button is the soft stop and the red button is the hard stop. So if we have an emergency, someone's on the telescope and it starts moving, something like that, the soft stop will put the brakes on sort of gently, and the hard stop will cut the power to the motors immediately. On top of that, we have this little tiny red button over here, which looks very scary, but all it does is unlock the doors. I think honestly that they just wanted a big scary red button to put in the control room. They didn't really care what it did. When I bring students into the control room, they always ask what it does. And I always tell them that it, makes the telescope explode or something, but it doesn't, it just unlocks the doors. Over here, we have the observer annex. So most of the time, our observers, like the scientists that are getting data on our telescope, they can tune in, right? They can log in from anywhere in the world. So they can, be on their couch in Dubai and operate the telescope or use the telescope from there. But there are some people who like to be on site when they're getting their data. Most of the time, these are just scientists who are employed by the observatory who are already here. But there are some people who, want to do observing on site, and that's perfectly fine. However, our observers have a tendency to look over our telescope operator's shoulder all the time, and the operators are not big fans of that. So we have a little annex over there out of our operator's way to make sure that they have some place to be, so they're not trying to mess around with the operators computers. So when I take people up on the telescope, I start them from the bottom and go up. So that's what I'm going to do with you guys. Starting from the bottom is the foundation. The foundation of the Green Bank telescope had to be very, very sturdy. Number one, we had to be really well grounded, right? We get struck with lightning about half a dozen times a year. And two, this is a 17 million pound moving object, right? It needs to be very, very sturdy. So our foundation is 20 feet of reinforced concrete onto solid bedrock. And then in the center of the foundation, coming up from there is the pintle. So because this telescope can move left to right, we needed a place for all of the cables to go through, right? Because if you just wrap them around the outside, something's going to snap. So all of the cables go in up through the pintle area. We have what's called the azimuth track. So when I say this is the world's largest fully steerable radio telescope, that means it can point up and down and left to right. So left to right, it can actually move 360 degrees in 9.5 minutes on these giant trucks that hold the telescope up. So here's a GIF of it moving. This is sped up, obviously. Takes 9.5 minutes to move it in a full circle. But this is how we can turn the telescope in azimuth, or left to right. On the first floor of the telescope, we've got a whole bunch of different sort of rooms. Over here, we have the heating and air conditioning units. These blue rooms are our power generators, our backup generators. So if the power goes out, this telescope is hooked up to the grid just like your TV is. So we sometimes, the power goes out unexpectedly. And if the telescope's in a precarious position, we need to be able to move it to a safer position. So we can turn on those generators and they will generate enough power to get the telescope into a, sturdier position than, hanging over.
It's up there.
Over here, we have the servo room. So this is where all of the computers and that sort of thing are. I will ask that everyone's muted themselves, just so everybody.
This is the astronomy meeting. Oh.
There we go. So just so everyone can hear me a little bit better. So we have a problem with interference, right? And that is that anything that uses electricity is going to give off a little bit of interference, right? But we need these generators, we need these servers, we need these motors on the telescope. So what we do is we actually will put all of this machinery in a Faraday cage. A Faraday cage is just a grounded metal box that is RFI shielded. It is shielded to make sure that none of that interference can escape and get up to the telescope, because it would be dumb to spend, $75 million on a telescope that can only pick itself up. That would be like having eyeballs you have flashlights permanently attached to your retinas. It just wouldn't really work too well. Here we have some more safety procedures. We have e-stops or emergency stops everywhere on the telescope. If you are on the telescope, you are within arm's reach of the emergency stop, because we don't want someone to be on the telescope and then it starts moving. On top of that, we have a lockout system. So when someone goes up on the telescope, they're given a little lock and they'll write down their name and what they're doing on the telescope. They will lock that into place. And then the telescope cannot move until all of the locks have been removed from this sort of key here. And that, make sure that helps us make sure that nobody is going to get flung off the top of the telescope. I do have a physics degree, so I managed to do some kinematics, and it turns out if you're at the top of the telescope and it starts moving at full speed and then it stops, you'll get flung 26 feet, which is a little disappointing. I was expecting it to be like hundreds, but what can you do? We're going to go up the elevator. This is all the way up to sort of the center of the base of the telescope. This is the bull gear, which allows the telescope to move up and down, or in elevation. So we can move left to right and up and down. We've got a 90-degree range, so from 5 degrees above the horizon to 95 degrees. And when you're looking at the bull gear, you'll notice that it's not actually symmetrical. One side of the bull gear has all of these sort of metal plates on it. And these plates are counterweight to the receiver arm. So we've got this giant receiver arm on one side of the telescope, and that weighs a lot. So we have bolted a whole bunch of counterweights just made out of metal to make it a little bit more sturdy, right? So the whole thing doesn't fall over. In the center of the bull gear, there's this little tiny pin. It's about, a couple feet by a couple feet. And when we enter this pin into the bull gear, the telescope cannot move up and down. And we always do this when something is going up, when somebody is going up to the top of the telescope, because we don't want anything, again, we don't want anyone flung 27 feet off of the telescope. Like I said, we can get to around 5 degrees above the horizon. This is the most that any telescope, this is the closest that any telescope can get to the horizon. So using this up and down and left to right method, we can cover 85% of the celestial sphere in a 24-hour period. This is the most of the celestial sphere that any telescope can cover. So we can get very, very close to the horizon. When I say that's the most that any telescope can cover, of course, I'm not including like space telescopes like Hubble, anything like that. They don't have to deal with the horizon. So in my opinion, they're cheating. I'm sure space telescopes might have other opinions about that, but they're not giving this presentation. So there. And this is what we call snow dump position. We're in the middle of West Virginia, right? We get snow a lot. And we like to be able to keep the telescope clear of snow because it gets pretty heavy, right? So we'll dump it into what's called snow dump position, depending on how quickly the snow is accumulating, right? But sometimes the snow is like, it'll stick to the dish a little bit too much. So what we do in that situation is we find an intern or, you know, someone who hasn't worked here for a while, and we'll send them out and tell them to just like sort of tap on the dish, and then the snow all falls on them, and it's very funny. We can also just move the telescope, shake it side to side, but that's not as fun. Going up to sort of the fulcrum of the telescope, we have the actuator room. So the Green Bank telescope's dish is made up of 2003 panels. And each of these panels has an actuator or motor that can move up and down on each of its 4 corners. So we can move that, move each one of the panels individually to maintain the most perfect parabola that we can get, or partial parabola, excuse me. Now, each of these
That kid's good. See?
each of these actuators can control the height of the panel to around 3 widths, or 3 widths of a human hair. So it is very, very highly sensitive. And each of these actuators requires a little computer to work. So we have basically little Raspberry Pis in the actuator room. They're all RFI shielded, and these will protect, so they're protected from giving off interference, and they tell the telescope what to do. They tell each of the actuators to go up, down, left, right, you know, whichever, or just up and down, sorry. We're gonna walk across the catwalk. I keep trying to get our PR person to try to get America's Next Top Model to do a challenge across our catwalk. I think it would be fun. Nobody listens to me though. But then we're gonna go up a second elevator. Now, as you're watching this video, you'll notice that the elevator is going sideways. And then you'll also notice that in order to get in and out of the elevator, you need to move one door that's horizontal and then a second door that's vertical. We hire the best and the brightest here at the Green Bank Observatory. So people keep forgetting to close that second door. And when you just send the elevator up without closing the second door, it breaks. So there's a good chance that if you ever come up on the telescope, you're going to have to climb some stairs to get up to the receiver room. But what can you do? The dish, like I said, 2.3 acres, about 6 Olympic-sized swimming pools or 2 college football fields. Now we build dishes. We build giant dishes because the bigger the dish, the more sensitive the telescope. This is true for optical dishes as well, optical mirrors on your optical telescopes. Because if you have a bigger dish, you can just collect more light, right? We've got a subreflector. So radio waves will come down from space, right? They'll bounce off of the dish into the subreflector, which is this 8-meter wide dish, and then into the receivers at the top of the telescope. But when you're looking at this telescope, you'll notice that it's a little, you know, off, right? It's not symmetrical. And that's for a reason. So right here we have the Effelsberg telescope, excuse me, in Effelsberg, Germany, which is a 100-meter telescope, just like the Green Bank telescope. And it has a sort of classical mount, like the Gregorian parabola that bounces radio waves up into the receivers. Now, I'm going to get a little technical here. When you are building a telescope, you have to worry about quantum mechanics because you're trying to detect light. And one of the biggest sort of ideas in quantum mechanics is this idea of the double slit experiment. If you have radio signals or light signals or whatever coming in from space and you pass them through a double slit, you don't get 2, you know, bright marks. You end up getting 3 because of this weird sort of lobing situation. We've got destructive interference. It causes a bunch of issues. So we get this weird sort of pattern. Now, this picture might look familiar because this is also how most people set up a telescope, right? You have your giant dish, and then you have the receivers at the front. And this causes some distortion in the image that you pick up because you get all of these like little lobes of distortion, of interference. Now, ideally, we would be able to move that receiver to the top of the telescope. So we would have this unblocked aperture. But if you do that, radio waves are still just going to bounce to the focal point, right? They're not going to go into the receivers. And that's the entire point of a telescope, right? Is to funnel all that radio energy into the receivers. So what the Green Bank telescope does is it actually has a half parabola. We built half of a parabola to create this unblocked aperture, to create this unblocked dish, which means that we can have a more sensitive system. So looking at the Effelsberg telescope, same size, same receiver, same wavelengths, this is the difference in data that we can collect. So this is the Omega Nebula in X-band, using the exact same amount of time, the exact same data analysis tools. This is just the difference in resolution we can get with this unblocked system. So we can just do better science. And it's actually really fun because this was we were the first major facility to do an unblocked aperture. And we have had such success with it that now you're seeing a whole bunch of other observatories when they're building their latest telescopes, they're all trying to get this unblocked aperture as well. They're trying to do this weird sort of clam-shaped dish. In fact, the Very Large Array in Socorro, New Mexico, the VLA, is working on its next generation VLA, the NG VLA, and all the antennas for that system look like little tiny GBTs. It's really fun. The Green Bank telescope is, of course, the original. But, you know, it's nice to have little tiny GBTs everywhere. We've got about 8 receivers on the telescope at any given time. And each of the receivers can detect a different wavelength. So if you want to look at a little tiny millimeter length observation, you're going to need a little tiny receiver. If you're looking at an ultra low frequency, wide wavelength, signal, you're going to need a larger receiver. So we have all of these receivers in this sort of merry-go-round turntable turret sort of situation. So if I want to take an observation in X-band, we can move our X-band receiver into place. And if the next observer wants to do an Ka band observation, we can move that Ka band receiver into place. This means our telescope technicians do not have to climb 688 steps every time we want to do a new observation. But we run into a problem here, right? So most of the time when we have something electronic that's going to give off radio interference, we can just put it in a Faraday cage and call it a day. But you can't put a receiver in a Faraday cage because if you put it in a Faraday cage, it's not going to receive anything, right? And we want to increase that signal to noise ratio as much as possible. So what we do is we can actually cool our receivers to around 7 degrees Kelvin. Most of them are at 7 degrees Kelvin. Our Mustang receiver, which I think is this one right here, gets down to 2.4, I believe. And how we do this is with compressed helium. So if you guys remember all the way back to chemistry class, the ideal gas law is that if you have the same amount of gas and you increase the volume of that gas, you're going to decrease the temperature. And if you increase the pressure, you're going to increase the temperature. Yeah. So what we do is we can pump a lot of compressed helium into our receivers, increase the volume, and then pump it out, compress it somewhere else, then pump it in again. And we use this closed circuit sort of situation to cool our receivers down, slow down that molecular motion, and keep our receivers as radio quiet as possible. We have some of the best receivers in the world. We have some of the best receiver technicians in the world. And we are constantly getting, you know, other observatories asking us to build their receivers for them. And for the most part, we will comply. We'll do that for them. When the VLA, the Very Large Array in Socorro, New Mexico, asked us, however, they wanted 64, and we said, we'll help you design it. We got other stuff to do. So we got all the way up to the top of the telescope, but we could go down the elevators, but I would like to go down the fun way. This is how we paint the telescope. It takes about 10 years to paint the entire structure. We get a bunch of painters every summer who do high ropes training. They do safety training. They do rescue training, and then they'll get up to the top of the telescope. They will pulley themselves up and paint the telescope for a couple hours, come down for lunch, and then go back up and again and paint the telescope for the rest of the day. I love watching our painters because they're always, you know, big, you know, strong, tough guys, like 7 foot tall, and then they go up 300 feet in the air. And they just look so tiny. So that's what I have for you guys. We've got some time for questions, comments, anything like that. But thank you guys for inviting me to talk with you guys today. Do we have any questions? Oh, I see something in the chat. So the image was of the Omega Nebula. It was not Cygnus A. Yeah, Gary, what's up?
What wavelength range is?
Yeah,
does the
so we are
telescope handle?
100 megahertz to 100 gigahertz.
Okay.
So we can detect about a millimeter in wavelength to about a meter in wavelength. And then of course there are, you know, spots within that band that we can't look at. Like we don't have anything that can detect the oxygen line because there's oxygen all around us. So we wouldn't be able to detect anything. We would just be looking at the atmosphere at that point.
Yeah,
But for the most part,
but you
sorry?
would, for example, what you can see would include the 21 centimeter line.
oh yes, absolutely. That is one of the major components. I think like 30% of our observations are looking at neutral hydrogen, which is at 21 centimeter, 1420.41 megahertz wavelengths. Anyone else have a question?
I have a quick one. Maybe.
Yeah, what's up?
So are you down there now?
Yeah, I am.
Reason I
am
ask-
next door.
Okay. The reason I ask is I have a, to me, a golden opportunity. I've been working with Dan Reichert there for, what is it? ERIRA? The
Yeah,
Educational Research.
ERIRA, yeah.
Agency. We just heard the 40-foot is the power's out.
Yeah.
Is it? Do you know?
So the
probably
40-foot
headed up to-
telescope got struck by lightning recently.
Okay.
We are working on it.
I hope so. That'll cancel
What
it.
I
That'll
what I have,
cancel it.
we do have the 20 meter up and running for you guys to use. The 40-foot, I have been hounding Pete Chestnut all day, every day to get it up and running again. But apparently the $2,000 telescope from 1962 is less of a priority than the $75 million one
No
that
doubt,
brings
no
in
doubt.
brings in the money. So, and we have a bunch of I think the problem is we have a bunch of mechanics on vacation this week. So they're trying to get it up and running. They've told me by next week, but
That would be awesome. I'm really looking forward to that trip. It'd be
yes,
great.
absolutely.
It'd be great to meet you and see you down there.
Yeah,
I'm helping out the camp, and I just thought it'd be great to see this stuff.
yeah. So Jim is talking about one of our, you know, bajillions of educational groups that will come and visit us and use. We have a 20-meter telescope that can be used remotely, and we have a 40-foot telescope which can be used in person. The diameter of the Green Bank telescope is 100 meters by 110 meters. It's about 360 feet. The 40-foot diameter is 40 feet. The 20 meters diameter is 20 meters. I love questions like that because the answer is in the name.
Yeah.
Any other questions?
You're green, where are you located again?
Green Bank Observatory.
Bank?
Bank, B-A-N-K.
Okay. I'm trying to text my grandson. Oh. Tell him what he's missing tonight. He just started getting interested in astronomy.
Oh, good.
Yeah.
So Jamal, the dish is not circular, right? It is a partial parabola, so it's sort of a clam shape. Oh, what? Yeah, anyone, do we have any questions from Butterworth? Oh, we
Yeah.
got someone coming up. What's up?
If you can hear me though.
Yeah, I can.
Asking about your plants going around there. Do you have a way to control things such as people driving nearby with cell phones that are in operation? How do you handle interference, stuff like that?
Yeah, so we have two main methods. We're working on a third, but the main thing that we do is we will take, when you're looking at an object, instead of just looking directly at that object, often what we do is what's called a daisy scan. So we'll look on it and off it and on it and off it and on it and off it and on it and off it. So this is what your eyeballs do as well, right? If you're looking at a star, the only reason you can tell it's a star is because you're comparing it to the blackness of the rest of the sky. So what we can do is we can actually subtract the on object signal from the off object signal, and that gets rid of a lot of, telephone wires, cables, power cables, that sort of thing. The second method that we have is called integration. So we don't, take instantaneous data. We will average it over a period of time, and that gets rid of a lot of the like super quick bursts of energy. So that takes care of, bursts from signals like spark plugs, that sort of thing. The on and off sort of method will take care of, constant interference. So telephone wires, that sort of thing. And then the third thing that we're working on is, AI mitigation, right? The idea is that computers should be able to remove or at least alert an observer when there is interference in their data. We don't have, it's really, really difficult to take out interference unless you know exactly how far away, what frequency, what very specifically is giving off the interference. It's really hard to figure out what's supposed to be underneath that.
Okay.
But we are working on methods to alert our observers, say maybe you want to take a second pass at that because you got some interference in your data. Jerry, what's up?
Actually, very basic question is, are your receivers actually point receivers, or is it an array of receivers like a CCD?
Yeah, so we have we actually have three different kinds of receivers. We have the classical feed horn, right? That's just, it looks like a cone. We have the bolometer receivers, and a couple of our bolometer receivers are in arrays. I don't think we have like a single bolometer receiver. And then we do have what's called a camera. So I think we have a couple of receivers that are multiple feed horns. A camera in radio astronomy is 4 to 150 pixels. So we have Argus, which is 144 feed horns. And that's the most you can really get. That's 144 pixels, right? But when you're getting into like higher frequency, you can do that sort of camera work. When you're looking at really low frequency, that feed horn needs to be the size of what you're looking at, right? So it's really difficult to build, a super low frequency camera because you need like physical space for those feed horns.
Well, the pixel would have to be of the order of a wavelength at least.
Yes.
And if you got low frequency, it's going to be it's going to be a big pixel.
Exactly. So most of our receivers are just 1 pixel, right? And we'll just move it left to right, and that's how we map things. Argus is, I want to say X-band, but that's probably not right. It's looking at ammonia, so the ammonia line, the NH3 line, which makes it really good at tracking star formation. But you couldn't make a camera, at least not for our telescope, for the 21 centimeter line, right? Because you need a 21 centimeter.
But X-band is only about like 8.
Yes. Any other questions?
Now to give you electrolytes.
So what is the future hold for project here at Green Bank? Is there anything in process right now?
Yeah, so I'm going to put a link in the chat of our schedule.
A couple pieces on
Right now, we're mostly doing maintenance. We got maintenance going on right now because during the summertime, that's the best time to, work on the telescope. So let's see what we're doing. Right now, we're doing overnight painting. That's exciting. Now, when we do overnight painting, we don't stop observing. We'll just leave the telescope running, and then whatever, passes in front of the sky or passes in front of the telescope, we'll just take data of that. We can use that to look for fast radio bursts. We can use it to look for pulsars, that sort of thing. Breakthrough Listen is a SETI initiative, so searching for extraterrestrial intelligence. We recently signed our first 5-year contract as an observatory. So that's not part of the National Radio Astronomy Observatory. So in 2016, the NRAO divested from Green Bank and we became our own institution. So we just got our first 5-year contract from National Science Foundation, which is really exciting. So we're going to be running for another 5 years at least. But I mean, the future is really exciting. We have a brand new telescope that we're building called, that's a CHIME outrigger. So the Canadian Hydrogen Intensity Mapping Experiment in British Columbia wanted to make an interferometer with us. So we said, absolutely, use that empty field over there. We also have a new data center because in 2020 alone, we gathered 166 terabytes of data. We need some place to put all of that. I personally am looking at the next big thing from radio astronomy. I think is going to come from the data analysis front. Because it's not like we can do new wavelengths. It's not like we can do, new, we have pretty much the best physically possible telescopes. I think that the data analysis is really the place to look right now. But if you had a gun to my head, the next big thing from radio astronomy is going to be a nanograv project. So nanograv is a project that is looking for super low frequency gravitational waves, and they are like weeks away, in my opinion, from getting a positive result on that. They've been working on it for like 20 years, and they're really, it's a really amazing project. Not only because they're doing gravitational research, but also because they are part of the Pulsar Search Collaboratory, which takes high school students and gives them pulsar data and says, hey, you know, look through this for us, do this with us. But that's what I would say. It's a super exciting project.
Good. Any other questions for our guest?
So the project you just mentioned, is it using this radio telescope?
Yes, so a nanograv is a project that is, so let's start from the beginning. The Green Bank telescope is the world's premier pulsar observatory. We have discovered more pulsars than any other observatory by an order of magnitude. A pulsar is, of course, a rapidly spinning neutron star that gives off a very distinct sort of blip, 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 blip signal. And they can be used as timing devices, right? So they are very, very precise. So we can use them for a whole bunch of different sort of tests of relativity in space. We can use them to figure out how time is working. So the idea here is that if you get an array of pulsars and you can tell that a whole bunch of pulsars in one area slow down and speed up at the same time, that means that the distance between us and those pulsars got a little bit longer and then a little bit shorter. And we call that a gravitational wave. So the idea is to create a pulsar timing array to track these sort of gravitational waves. They have, if you look up the mass of Jupiter and you see a whole bunch of significant figures, right? We know Jupiter's mass with a really high degree of accuracy. That is how they, that is how we know the mass of Jupiter, is because when Jupiter is in front of a pulsar, it bends space-time just a little bit, and then we can do the math to figure out, because it bent space-time this much, it has to weigh this much, or it has to have this much mass to it. Anything else?
Just a comment. That sounds real cool.
It is, doesn't it? I'm a big like relativity fan. I don't know how that sounds to like normal people, but you guys are in an astronomy club, so I'm sure you'll understand my.
So do you have a permanent RFI engineer for your telescope?
Oh yeah, so we are the RFI observatory, right? So we have our main sort of RFI coordinator is named Carla. She is also a yoga instructor, but she designs a lot of Faraday cages and the cryogenics that we use. And then we have specialized scientists for our RFI as well. Pasi Ghosh is a really well-accredited sort of radio astronomer who retired to Green Bank and is now working only 40 hours a week to work on RFI. He's one of those people.
So do you need this engineer, RFI engineer, only during the design phase, or during the whole time that the telescope is operating and running? And
so most of the software stuff gets written by scientists and not our engineers. The engineers are more focused on maintaining and upgrading the telescope, and the scientists are, their job is to make sure that people get the best science result that they can. And yeah, you don't really want engineers messing around with your data, because they don't, number one, they don't really know what they're looking for, so they could just like erase something that you want, but also because engineering, like the engineering sort of idea would, try to put this delicately, our engineers are very good at what they do, and we're gonna keep them doing the best thing that they do, which is, you know, stopping RFI before it shows up. Our scientists have a lot more experience in the data analysis, in mitig and that sort of side of things. Anything else?
A very tactful explanation.
Thank you.
Yeah, talking to an engineer.
I had a feeling I was talking to a lot of engineers in the room.
Just one,
And
and
an
one last
occasional
thing.
quantum mechanic.
Oh, gotcha.
One last thing I wanted to ask is that, so as far as our RFI goes, you're not concerned only about the electronics and the antenna. You're really also concerned about interference and the data that you collect from space. Is that correct or not?
So the number one cause of interference that we get is from the community. We have I can put this in the chat as well. We have actually, let me just share my screen. A list that we maintain of interference that, let's see, this is one of my favorite tables because people always, you know, are updating it with just crazy things that show up in their data. So, you know, emergency services, that sort of thing, weather radio, RFI, that sort of thing. The active surface itself gives off a little bit of interference. We have somebody's doorbell apparently has caused enough interference that it's gotten its own entry here. But one of my favorite sources of interference, if I can tell a little story, was 2007. The National Forest Service decided that they wanted to do a study on the migration habits of flying squirrels, of the eastern flying squirrel. So what they did was they got a couple dozen flying squirrels, put GPS tracking collars on them, and released them into Monongahela National Forest, right next door to us. And these GPS tracking collars transmitted so powerfully that when we used our telescopes, we could only pick up the squirrels. We couldn't pick up anything else. So this shut down observations for 3 months. We could not do a single observation for 3 months because of these flying squirrels, which is absolutely hilarious to me. We did have a conversation with the National Forest Service about that, and they now do all of their tracking projects in other forests.
What happened to those squirrels?
So we just waited for the GPS tracking collar batteries to die. But this was back in 2007. So I don't think those specific squirrels are around too much longer. I hate to say. I'm not quite sure about the lifespan of flying squirrels though. So if anyone is a flying squirrel expert, feel free to correct me on that.
Any other questions for our speakers tonight? Well, thank you very much. This was very interesting. You've had a nice presentation and good stories.
Yeah, thank you for having me. And maybe I have to come back and do a site tour with you guys.
Sure.
Yeah.
Thank you very much.
Thank you. I'll see you guys
Thank you.
later.
So you're welcome to stay on. Lucy, anybody that wants to stay on can. I have a couple more items here. Let me see here. I guess I'm not sharing that. Hang on. Okay. There we go. So as far as our club activities, upcoming events, July 17th, which is this Saturday night, we have a public outreach session at Niabi Zoo. Is it going to rain?
It's supposed to rain for the next 6 days.
Well, if it's raining, we won't do it, but that's our schedule anyway. For those of you that may not know, we have scheduled every third Saturday every month. We have public outreach sessions that we do at Niabi Zoo, which is a local zoo here, which is a very nice place, central place that people know about. We set up scopes and we have our mobile observatory that we bring there. But this Saturday is hoped that we can do it. So we'll have to see. The weather has not been very cooperative here. The Quad City Astronomical Society has a meeting July 19th, so that's next Monday. And I don't know if, is there anybody from QCAS that would want to talk about that, what the topic is? Jeff, are you on the line?
Yeah, I'm here. I don't know what Robert's got lined up for that. They had a few things they were talking about.
Okay, you'll be sending out, or he'll be sending something out in advance of that, so we'll be watching.
Yes.
We have a request from the public on July 31st, Silver Bell Hollow. That's a farm out by Illinois City, and they raise alpacas there. It's really neat. We've been there. When were we there? Like two or 3 years ago. It was 2 years ago. We were there. It's a nice place. It's out in the country. It's fairly dark, and the llamas are cute. You can pet them. You know, and then you can observe while you're petting the llamas. But we'll be there July 31st, unless it's raining. So we'll have to see. And then the next thing we have here for QCAS is a public night at the Jens Wendt Observatory.
That'll be at Menke.
That'll be at Menke. Okay, so yeah, I got that wrong. That's going to be at Menke.
Well, actually, you don't have it wrong. When the club moves over there, we'll probably have to do some kind of combining of names, because we'll have our observatory over there too. So you're technically right. The location though is over. They're all over at Menke from now on.
Okay, good. That's good. That's a nice location too. So that's July 31st. So actually, July 31st, you got a choice. You can go to Menke or you can go to the llama farm. And then you have the meteor party for QCAS on August 7th.
Correct. And that's at the Pleasant Valley Junior High so far. That's where we had the last two. And the last one we had about 400 guests show up. So it's a nice event. We need to double check with the school system to make sure that they don't have any pandemic requirements. Right now, it seems like it's all normal, but who knows what happens in the next month or so. So, but it's a fun time.
Okay, thanks. Yeah. The next PAC meeting that we have actually will be a picnic. And we're going to have that at our Paul Castle Memorial Observatory south of Milan. That's a picnic and observing session, hopefully, and as well as a meteor shower observation event. And that's on the 14th. And Wayland is here. Do you want to say anything about it, Wayland?
Meet at 6:30. Bring dish to pass, your own meat or whatever. There will be a grill available. Whatever else you want. Beverages, as long as they're non-alcoholic. And that's basically it. Something comfortable to try to either observe or watch meteor shower when he's going on.
Okay, thank you. And then you have the Menke Public Night, August 14th as well.
Correct.
And then the QCAS meeting, the next meeting there will be the 16th of August. And then further down the list here, we have another Niabi Zoo outreach session, August 21st, that third Saturday in August. And then further down, September 13th is our PAC business meeting and smorgasbord. And this is an event where we have people basically from the audience, PAC members, most of them will be making short presentations, maybe 5 minutes or maybe 10 minutes in length or shorter. I've got one name down there, Charlie Miller. He's actually not a member of the club, but he was in attendance at our last meeting that we had here and told me about a homemade planetarium projector that he has, and he would like to talk about that. If there's other topics anybody has that they want to talk about, and it could be virtually anything science related, astronomy related, Dino Milani is our vice president is going to be scheduling those other topics. Does anybody else have anything? Did I get everything down here? Or are there any other?
I guess I did want to mention that our 20-inch Newtonian is now over at Menke Observatory, set up and ready for use. And I think they were doing a little bit of imaging with it. And Rusty was over there last Saturday helping us beef up the pier a little bit. So we still have a little bit of work, but it's great for visual, and it's a beautiful scope to work on. And we've got that inside the Menke roll-off building. We pulled out the old 2 scopes they had there. So we've got that nice 14-inch SCT, and we've got the nice 20-inch Newtonian now set up for use.
Cool. Anything else? I think that's all I had here, other than some objects that folks have imaged in the last month since our last meeting.
And that is an 800 millimeter. I looked it up.
800 millimeter focal length.
Yeah.
So Rusty, these are your images here.
Yep.
Let me. Okay, can you see that?
Yeah. Oh yeah.
Okay, you want to tell us what this is?
Well, on the maiden voyage, I got a new telescope. It's Orion 8-inch Newtonian astrograph. It's a f3.9, 800 millimeter. So I took it out and got it all set up and tried my luck, see how well I could do, and got this is a picture of Denham. I just took it just to see how it would turn out, and I was kind of, well, starstruck. It was good. I was amazed at that picture. That was just so cool.
That is nice.
Yeah, I love the spikes.
Yeah. And there's M13. I was in all the stars that are there, with my CPC at the 11-inch CPC, I don't even see anywhere near that many stars in that thing.
Well, that's the difference between a F3.9 and
Yeah.
F10.
Yeah. Oh, yeah.
And I see you got some satellites here too.
Yep.
Nice.
Yeah, that's the Omega.
Yeah, so we saw what that looks like in radio. It doesn't look the same in optical.
No. It is a little different. And that's the Trifid.
Yeah. Nice.
M51.
Nice. And that's the Ring Nebula.
Ring Nebula.
Oh, you can see the central star too. Nice. I like the
Yeah.
pink. Oops. And then.
Yeah, this was the moon. It was just coming up when we decided we better get ready to go home, which was at what, 3:15?
Yeah,
Mark?
around there. It was late.
It was. Yeah, my wife called me on the way home.
Mine did too.
But that was just above the treetops, the moon.
Nice picture, Rusty. And I see Steve left the room. He had this picture of Witch's room.
Yeah.
That's pretty nice.
Yeah, I had a lot of help from Byron too, getting that all set up. So.
And I'll just go up the list here. Roy, you sent some pictures.
For M13.
M13. Now, what did you use for a telescope here?
Well, it's called a Stellina. It's an observation station that once you set it down on the ground and turn on, it creates a Wi-Fi system, Wi-Fi hotspot. And then you control it from your phone. It reads a GPS and the date and time off your iPhone or Android. It has built-in star plates that identifies where it's at, where the sky is. It autofocuses itself, and then you tell it where to go and start taking pictures of it, track it, and it stacks an image every 10 seconds. Every 10 seconds, takes a picture and stacks it.
Cool.
So is this the scope comes from France?
Yeah.
Yeah.
The big thing you have to remember is you have to remember a long chair. So you can sit down next to it.
Oh.
Relax.
It just does it automatically.
Yeah, it does it automatically.
And you got the Witch's room here too.
Yeah.
That's really nice. A lot of color there.
I missed it. Which telescope is that? Is that Stellina?
Yes, yes.
You like it?
Oh,
The pictures are great.
yeah.
Yeah.
And this is just JPEG. I haven't done anything with the PITs because I can download PITs at the same time, but I haven't done anything with the raw. This is JPEG.
How many megapixel is that?
You know what? I can't tell you right now. I used to know what I do.
Looks pretty good though.
M51.
M51. You really got a lot of you got color and a lot of resolution there. And what was this?
That's a North American nebula.
Oh, that's North American. Yeah. Cool. That's the dumbbell. Very nice. Was that the strawberry moon?
Then
Eagle Nebula. Nice. Excellent. So this is a new scope you bought.
Yeah.
I'm jealous.
Al's gonna have to get a new scope.
And I'll skip over mine. I'll go to. Byron, this is your M13.
Yes.
Nice. Wow, you really got a nice solid block on that.
There's your double cluster.
Very nice. And I can sense the spikes on that too.
Yeah, isn't that neat?
Yeah. It is. It's great.
There's your lagoon.
Yep.
That's when we were fighting that haze on the south side of Minky.
Yeah.
Yeah, you can see a little bit of haze there, but there's nothing you can do about that.
No.
Very
There's
nice.
your Omega.
Very, very nice. I like the color. You got some orange colored stars. You got the pink coloration.
Yeah.
I think it's nice.
And this one I really like. If you zoom that in, you can get that. You get a lot of color on this one.
Oh, yeah. I like the star up here too. It's a nice contrast.
Yeah. You got these the same night? We were both out there, right?
Yeah. Yep.
Yes, it did. Nice, nice work. And then I got a few I'll show you too. Mine aren't quite that good, but
Just from the trip now.
this is Mesa Verde.
Yeah.
And I set up my scope out there, and it worked for about a half an hour and then it died.
Oh no.
Yeah.
And I thought it was a scope, but it's not. It was a battery. So I got a new battery, so I'm sure it'll. I got to test it now and make sure, but I got a new battery. But this was a strawberry moon, and shot across. That's probably a couple miles over to a mountain. Coming up, and you can just see a tree right there. Yep, that's just by sheer luck. And this was in Zion National Park. That's believe it or not, that is Sagittarius.
That's incredible.
Yeah.
That's just with a 35 millimeter planet, focus.
How many seconds was it?
Probably about 15 seconds,
Yeah.
20 seconds.
Beautiful.
Yeah. And when you looked at it, you could see a lot of it visually too. It was really, it looked like clouds in the sky. It wasn't
Yeah.
clouds.
That's what it looked like when I was out in Nebraska.
Yeah.
2 years ago.
And even though it was fairly dark, you can see this mountain over here has a little bit of light on it. That's just starlight.
Yeah.
So that's what we don't get around here anymore. And here, this is a poor. I did a poor job of getting the two pictures meshed together, but these are two wide angle, 10 millimeter focal length, wide angle lens images put together.
I think you did a great job.
But it's just amazing. So I played with the camera, my scope.
That looked fantastic.
It was beautiful. And most of the time we were out there, it was cloudy though. There was just like 2 nights it was clear. So
And like around here.
just like around here too, but it was cool. Before we went out there, they were complaining about 110 degrees, 115 degrees, but when we were out there, it was cool. We had like right there, we had to wear a couple layers. It was cold. Of course, that's fairly high elevation too. I think that's like 9,000 feet elevation, so it cools down when the sun goes down.
Now, did you deal with weather when you were out there? I heard they were having a lot of, was it rain?
Yeah, they had rain. Actually, which park was it, Mom? Was it, I don't know if you're still on there, but Mesa, well, we didn't have any problems in Mesa Verde, but in Zion, yeah, I think it was Zion, they had a huge flood. And
Yeah, they had a flood the day after we checked out of Zion. They had a flood.
Okay.
So we were
but
lucky.
we were long gone.
we were lucky. Zion was really nice. If you ever go out there, there's 2 entrances into the park. If you go in the southern entrance, that's where everybody goes. And you had to ride a bus to go in there, and you had to wear masks and everything else. But the northwest entrance, that's one nobody knows about, and that's where we got those nice pictures of the night sky, and nobody cared about anything there. We were just out there having a good time. Anyway, anybody else have anything to show or share or observations to talk about? Oh, I did have one more here. The other night, we were out to, this was Tuesday night, wasn't it, Dale? It was Tuesday,
Yeah.
last Tuesday night. We went out to the observatory, set up. Now, it wasn't the best, but it's the best we've had for a long time.
Yeah, you can see the stars anyway, even though it's a little hazy.
Yeah. So that's Dale and I on either side, and Chad Potter in the middle. Chad's the school teacher we've been working with at John Deere Middle School.
So did he decide what kind of camera he was getting?
I don't know if he's decided yet. He was looking at that one fairly pricey one. And I showed him the R2 camera. We used that Tuesday night. And I was pretty impressed with the R2. It worked pretty easy to use, and we got some nice images with it. Yeah. And we used his Nikon camera. We used my Nikon camera. We got some decent images just with our cameras. That wasn't very good. And here's that's M22. This was taken through the observatory's 11-inch CPC. And that's a Whirlpool Galaxy, but I think we were looking through some P-soup.
Yeah.
And then we were going for some of these globular clusters, which are nothing fantastic. But these are all the ones in the list of globular clusters that the astronomical group has. Some of them are pretty small. Anyway. Anybody else have any observations? Well, that's all I got. I want to thank everybody for attending. Yes, wish you all a good night and pray for clear skies.
Hopefully this weekend.
Yeah.
Hopefully this weekend. Yeah, come on out to Niagara Zoo if it's clear.
Hey, now I haven't talked to you for a while. Hey, how you doing? Good. You're looking good. Yes.
All right.
Okay. Well, have a good evening, everybody. Yeah. Thanks again.
Wow. You're supposed to say I'm looking good too.
Night.
Night.
Bye, everyone.
Bye-bye.
Bye-bye.
Oh, no. Oh. Okay, kids. Well,
Yeah. Here's that.
your head wasn't too bad.
Wasn't it?
When you turn, you can see